Hello, my name is Vladimir Gordiychuk. I represent the Makers company, and today I would like to tell you about computer simulation of Permafrost thermal regime under the influence of engineering constructions. There are many permafrost-related issues. Some of them are affecting the construction industry, reducing rates of development in permafrost regions. For example, a typical result of interaction between permafrost and engineering construction is permafrost thawing and consequent load carry capacity, reduction of load carry capacity. This may cause uneven soil settlement and structure deformations. That is why permafrost temperature is a key factor of structure reliability. We are working in the field of heat and mass transfer, in particular permafrost temperature simulation under influence of engineering constructions. Now I would like to tell you about our achievements in computer simulation. Well-known and widely accepted method for thermal analysis and simulation is based on solution of heat equation. A heat equation is used in a wide range of modern computer simulation software. Finding a solution of heat equation in 3 dimensions is a complicated and computationally difficult problem to process, and I will explain why it is so complicated. When dealing with permafrost, it is necessary to consider ground thawing and freezing processes. Mathematically speaking, it is necessary to consider water, ice, phase transitions that take place in moist permafrost. Phase transitions make initial heat equation highly nonlinear and especially difficult to solve using common multiphysics computer simulation software. It is usual when modern design engineers are dealing, have to analyze reliability of permafrost under large-scale constructions that are going to be operated during a long period of time. Thermal simulation problem is difficult, and it becomes even more complicated when dealing with large spatial and temporal scale domains. Considering busy schedule of a design engineer, it is important to perform computer simulation in a reasonable time. Computer simulation is performed by using numerical methods, thus implying an approximated 3D model to be used, called mesh. Mesh consists of a large amount of simple elements, called nodes. The more nodes are used during the calculation, the more accurate solution will be obtained, and the more time it will take to obtain that solution. It is important to understand that complicated large-scale domains require a huge amount of nodes to approximate them accurately. Now let's take a look at numerical methods that can be used to solve heat equation and compare their accuracy and performance. First, I would like to analyze implicit form of the finite element method. The finite element method has a wide range of applications, and it is used in ANSYS, Console, Abacus software packages. The implicit form of a finite element method is valid for its unconditional stability and large time step. But there is an issue with the convergence. Due to phase transitions, initial heat equation obtains high nonlinear behavior, and the high nonlinearity of heat equation makes it harder to solve underlying system of linear equations. Iterative methods that are used to find solution for linear system require a good initial approximation. Otherwise, there is a chance that this iterative method won't converge or will take a very long time to converge. Usually, initial approximation is taken from the previous time step, and in order to make initial approximation precise, it is necessary to shorten time step, thus reducing the performance of the finite element method, the calculation. My point is, When dealing with highly nonlinear heat equation, finite element method has a severe reduction of performance. That is why we weren't really satisfied with the finite element method and continued our research. So let's see how the finite difference method is dealing with the highly nonlinear heat equation. The implicit form of the finite difference method has a similar advantages and disadvantages as implicit form of the finite element method. The only difference is that the finite difference method provides a simple matrix sparsity pattern and the underlying linear system, for underlying linear system, thus reducing computational difficulty. Also, it is necessary to mention explicit form of the finite difference method. Explicit form of the finite difference method has unconditional it is not necessary to solve a system of linear equation, thus computational difficulty is reducing even more. Also, explicit form of the finite difference method has another important advantage. The finite difference method can provide high rates of acceleration on parallel architectures, which modern graphics processing units implement, and this is achieved due to relatively small sequential part of the entire algorithm. Our company dedicated several years to research a thermal simulation problem, and most of modern numerical methods were implemented and compared. Finally, we came up with solutions that combined usage of both implicit and explicit forms of finite difference method is the best solution, and a brief description of this method is simple. The initial domain is subdivided into several parts, and for each part of initial domain, an optimal implicit or explicit form of the finite difference method is chosen based on complexity analysis. After that, calculation is performed. Proposed method is implemented and tested in Frost 3D Universal Software. According to test results, combined method provides a significant performance boost in comparison with ANSYS console and the Vector software, especially when modern graphic processing units are used for computing. Now we'd like to show several examples of calculations performed in Frost 3D Universal Software. This is an example of temperature distribution and unfrozen water distribution around pipelines. It's a large-scale oil transfer pumping station and sections of pipeline. These are very large-scale, relatively large-scale domains, and we have 22 millions of nodes in this example. This section of road, we have even more number of nodes. It's 45 millions of nodes in this example. And also, I would like to show you an example of frozen dam. Like mathematical model that was mentioned in the beginning of my report allows to take into consideration the influence of groundwater filtration on permafrost temperature distribution. The problem is that groundwater filtration also needs to be simulated. That is why our company developed solver for filtration equation based on Darcy's law. And with filtration equation solver, it is possible to perform coupled thermal filtration simulation. And the frozen dam, which we can see on this slide, is a good example of a coupled thermal filtration simulation. As we can see, dam has multiple freezing devices installed inside of it, and well, we have another slide here where it can be shown. Well, Freezing devices make the ground to freeze and prevents groundwater filtration. Currently, we already have solutions for nonlinear heat transfer and fluid flow in porous media, I showed before. And currently, we are working and developing a solution for soil settlement, structure displacement, stress, strain, and failure with regard to fixture, loss, gravity, and nonlinear thermal expansion. In conclusion, I would like to summarize my report. Computer simulation of permafrost thermal regime is important when designing constructions on permafrost. There is a number of issues connected with the computer simulation of permafrost thermal regime, high nonlinearity of heat equation, large temporal and spatial scale domains, groundwater filtration. And there are different numerical methods that can be used to solve heat equation, but only one of them is capable to perform necessary calculation accurately and in a reasonable time. And it is a combined finite difference method.